Was the last problem we did? We were very close to ending this problem, but let's review and recap what we did. Oh, thank you. And would you, William, you turn the lights off just above me, please? Okay, the last problem we did, we take a look. We took a look at the pictures because often these are very helpful to solve the problems. So initially, I had a tank of oxygen gas and I had a tank of helium gas in my storeroom at the scuba shop. And a diver comes in and says, "Hey, you okay?" Okay, says, "Hey, I want to do a deep sea dive. And I want a mixture at these partial pressures of helium and oxygen." So, okay, I can mix this up for you. The tank the kid hands me is 5.81 liters. So I know that I need to figure out my total pressure in the tank. And we were able to figure out the total pressure in the tank by going, well, I know that the number of moles, the total number of moles, has to equal the moles of the helium and the moles of the oxygen, because that's a true statement. And so I rearranged this equation, this one using PervNert, that the number of moles of oxygen has to equal PV over RT. And I rearranged PervNert here for my moles of helium, and that also equaled PV over RT. And for this scenario then, I know that my total number of moles has to equal PV over RT. And we were good with that, yes? And then taking a further look at it, well, we knew something was true about R and T. What do we know about R and T? They were constants. So at this point, I'm like, well, you know, truthfully, there's an eraser. Oh, there we go. Really, I don't need to deal with these. He's not diving into super cold water, so I really don't care about that. And just to make things more clear, I'm talking about the pressure of the O2 and the volume of the O2, helium, and total. Okay, so using this equation, I was able to create a new equation. Right, so based on that, I could replace my values by giving me the pressure total times the volume total had to equal the pressure of the O2 times the volume of the O2 plus the pressure in the helium times the volume of the helium. And based on that, we were able to calculate our total pressure. 9 point what? 06. Any questions on what we did with that yesterday? Wow, did that just totally make sense right there? Chloe? Vanessa? Yeah. William? Yeah. Where did I lose you? You don't know? Okay, never mind. Devin? Brennan?
I'm good.
Actually, I'm not good.
You're not good. Talk to me, Vanessa.
The NT equals...
The N total, the number of moles total,
equals
number of moles of helium plus oxygen. In this final tank, I'm going to have a total number of moles.
Yeah.
And in that tank, what are the two gases I'm mixing?
Helium.
Oxygen. So the number of moles of, think about moles for a second as grams. You okay?
Are you adding them?
I am adding them.
Oh, I look at the multiplying them.
No, this is addition right here.
Yeah.
Where? No, not
The-
right there. Like the one under it. I understand that one there. I don't understand that.
This one you don't understand. Okay. Did you understand this one?
Yeah.
This is the same thing. The total number of moles in the tank is equal to the total pressure in the tank and the total volume of the tank. I had RT underneath it, but since R and T were constants, I got rid of them.
Okay. I was just like, wait, what's that?
Nope, that's good. 3 points. Good question. Anyone else? Question? Okay. So then you just had, because we had all of these values available to us except for the total pressure. So then that was just a matter of plugging and chugging.
How many tests will we get pretty pictures?
Probably not, but you can draw pretty pictures. Okay, so from there then, the question is, well, what are the partial pressures of each of these gases? Because Dalton's law of partial pressure says the total pressure has to be equal to the pressure of the helium plus the pressure of the oxygen. And we just calculated this total pressure. But what I don't know is the partial pressure of the helium and oxygen. Are they going to mix and react together? Is the helium and oxygen going to react together? No, they're going to pass by each other going, what up? In the tank. They don't care. They just bypass each other. No big deal. So we can actually, since the volume, we can assume that the volume of those individual molecules are so small they don't matter. We can treat each gas separately. So we can totally and completely ignore this gas for a minute. Just ignore it, like it's not even in there. Because, you know what? Helium doesn't care about the oxygen. Yeah, what up?
So you could do the same as the other way around.
Right. So what we did to find the partial pressure of the oxygen then was, you know, hey, this is just like one of the earlier problems. We had an initial pressure, an initial volume of the oxygen, and we put it in the new tank, which gave us a new pressure and a new volume. Because I can completely ignore the helium. It doesn't care. Remember before problems we had, okay, we have gas under this pressure and volume, and I'm going to put it under a new volume. What's the new pressure? Do you remember we did that with Boyle's law? Way like the first problem we did. Remember those? Then it becomes exactly like one of those problems because the gases aren't going to mix and react. So I'm going to carry this problem here where I can actually work on it. So what is the initial pressure of the oxygen?
25.
No.
Oh,
Pressure. 1.3 atmospheres. And what is the initial volume of the oxygen?
27.
Equals. And what is the new pressure of the tank? 9.06. Pardonnez-moi. I'm going to erase that. That is not the new pressure. We don't know the new pressure of the oxygen. 9.06 is your total pressure. We're after this guy right there. We're after that one. We don't know it.
We know the volume.
We don't know that. Yeah. And so what's our new volume? Good.
Shouldn't it be the other way around? Because you're looking for the pressure of
You can-
helium.
I'm looking for the pressure of oxygen, honey. You could do.
Never mind.
Yeah, that's okay. So what is the partial pressure then of the oxygen?
6.13.
Good.
And then you just minus it from.
Yeah, now you can just subtract. Because we know the total pressure, 9.06.
You know, that doesn't make a lot of logical sense to me though, because if the volume that the oxygen is actually going to be smaller because it's not actually going to take up that whole tank.
No, it's more.
Gases will. They can fill the tank completely.
But it won't take up the whole tank if the helium's in it too.
Remember, in a gas, the distance between the molecules is very large, correct? And we are not compressing this gas so much that we're turning it into a liquid. And the assumption is twofold. The first assumption is the distance between the molecules is large, even if we put it in a smaller tank. Second assumption is the individual molecule's volume doesn't matter, which is why we can ignore the helium completely. Imagine for a second you're driving in Utah at 3 a.m. It's a really big state. Are you going to pass another car eventually? The distances between you are great, but it doesn't change the volume of that state. The volume of that tank is smaller, which is why we assume pressure is created by collisions with the sides of the container or with other molecules. So every time they collide, picture a pressure increase. So in a smaller tank, they're going to collide a lot more, which will bump up my pressure. But the space between the molecules is so big that even if I put it in a smaller container, it's still, the spaces are so big. More collisions, true. But the space of the helium molecule itself and the distance between them is still so small, it doesn't matter.
Can you convert, from okay, so if you have 27.4 liters of O2 gas form, can you convert that into how many liters would be in a liquid?
Yeah, I probably will need the density of the liquid to do it.
So, how much liquid would that be?
Yeah, I'd have to look. All right, are you better, Chloe?
Yeah.
If these gases do not react together, then you can ignore the other gas in the tank because oxygen doesn't do anything with that gas. It ignores it too.
I just figured though, because you have oxygen, and it takes up if you put it in that tank, it would take up the whole tank. But I felt like once you had helium, it has to make room for helium.
It doesn't, because the distance between them, you're thinking like liquids. You're thinking in our world, our real world, where if I take one liquid and pour it in, I take another liquid and pour it in, it raises the volume, right?
Yeah.
Gases don't behave that way. It'll mix evenly and completely and still have room left in that tank. They don't take up enough space individually to worry about the interactions with the other. Basically, you're pouring one and pouring another in and not changing the volume at all. You can't do that with liquids. They don't behave that way, but gases do behave that way. That's why very early on, they mix uniformly in the container, and they're easily compressible. The distance between them are very large, and the individual molecules are very, very small. So small we can ignore it. That's why it can behave this way. 5 points. Excellent question. Anyone else? Yes.
Okay, so, we set the equation equal to P1V1. Why are we using the liters of the last one and not the liters of each?
Okay.
It's a total.
Right. See here in this P1V1, P2V2 equation. Oops, I still have the eraser on. I'm sorry. I meant to still have this blacked out. Because these guys don't interact, when I'm looking for the new pressure of the oxygen, oxygen was sitting over here in this great big, where's my pen? Oh, there we are, in this great big tank. And the pressure wasn't very high, was it? No, it's just, that's almost the pressure we live in. Almost. Then I took this gas and shoved it into this little tiny tank. So what would you expect the pressure of the oxygen to do? Which it did. Now, a couple of you have already said, well, hey, we already have the total pressure and we have PO2, so we can just subtract, right?
Yeah.
Well, I want to do something else. And you're right, you could do that. But humor me for a second. Let's just look at the helium and ignore the oxygen. Can we do that? Let's just look at the helium and ignore the oxygen. Because we had helium in a tank, didn't we?
Yeah.
And we shoved it into another tank, and we're pretending like they don't interact, right? So here we had an initial pressure of the helium. We had an initial volume of the helium. We don't know helium's partial pressure, but we do know its new volume. So we had an initial pressure of the helium, which was 2, correct?
Yes.
Multiplied by 8.5. We don't know the new partial pressure of the helium, but we do know its new volume.
5.8.
What'd you get when you did that math, please?
I didn't do that. I did it the other way.
Please do it.
2.9.
Oh,
And that's what I got the other way.
Oh, that's what you got the other way?
Yeah,
2.93
exactly.
atmospheres is the partial pressure of the helium.
And do you write atmosphere of helium, or do you write just atmosphere?
I would say PO2 equals and PHE equals.
Okay.
Oh, so you mean even solving it using P1 V1 gives me the same as if I'd substituted 9.06 equals X plus 6.13. I get the same answer? Uh-huh. That kind of cool, Chloe?
Yeah.
Because it doesn't care about the oxygen. They pass by going, yo, what up? And maybe, you know, the highway in Utah, eventually it'll see another one. Hey, how you doing?
I like how you used it like that. That's
You like that?
that's good.
Yesterday I was watching How It's Made, and they had, like, for bacon, they, like, liquefied smoke and then injected it instead of having, like, smoke.
I've heard. I don't know how that happened. Okay, so yeah. So we have 46 liters of helium at 1 atmosphere and 25 degrees Celsius.
Since the atmosphere and the temperature stay the same.
Hold on a moment. And now I have a new tank of 5 liters and 1 atmosphere and 25 degrees Celsius. So, oh. So this is my new tank. Well, I'm sorry, because all my pictures went away. New. Old.
This will work with any kind of too.
So, do I have a before and after situation?
Yeah.
Okay, what should I do, Michaela? Any suggestions? Well, okay, so does the temperature change? Okay, I'm going to write perv nerd up here. PV equals nRT. Does the temperature change in this problem? No, so I'm going to get rid of that. Does the number of moles change in this problem? It doesn't say anything, so let's get rid of it. It doesn't say anything about moles, does it? Okay, that's good. Well, if R is going to equal before, then can't I have an R that equals after? So that means I can use P1 V1 equals P2 V2. And P2 is going to equal the new partial pressure of the helium. So solve for P2, please. Yes?
Yeah, what if you knew put the numbers in when you just put the B and the 1 and
Sure. So,
I know.
it's okay. So let's do the math on this one. So I'm going to rearrange for P2. P2 is equal to P1 V1 over V2, which equals 46 times, no.
Are we going to use helium O2 left?
Well, as the key is that the two can't react. And so it could be any of the noble gases. So P1 is 1 atmosphere. V1 is 46 divided by V2, which is 5. That's what you want to see, Nikki. I understand. Okay, so what's that equal, folks?
9.6.
You with us, William? 9 point what?
9.2, I got 9.2.
I got 9.2.
I think it's
9.2? Is 9.2 our final, thank you, answer. 9.2 atmospheres. Thank you. So I'm going to put that up here. So we know the partial pressure of the helium is equal to 9.2 atmospheres. Okay, now let's tackle the, what?
The O2.
The oxygen, okay.
I think this way is a lot faster.
Yes, but you have some problems on your homework where you do have to see some of the logic behind it.
Yeah.
Okay, so here we have, this is 12 liters at 1 atmosphere at 25 degrees Celsius. And we're going to take this oxygen and put it in the new tank. So I can use the same equation. Except P2 now is going to equal the oxygen. So the partial pressure of the oxygen is going to equal 1 atmosphere times 12 divided by 5. And what'd you get, William? I'm sorry? 2.4? Is William correct? Okay, good. So how do we get the total pressure now? Add it up, because the sum of the partial pressure is equal to the total pressure. 11.6? Oh, good. Questions?
I have a question. When we're trying to find partial pressure, will we always be able to use P1? P1?
No, what if the temperature changes?
I don't know. Okay.
If the temperature changes, then this would have a T1 over
But we can
T2.
always bank on P1, like we can always bank on P1 times P1 equals P2. If the temperature changes, we have to add.
Yeah, you start with perv nert and see what you need.
So that's always gonna work.
Yeah, always start with perv nert and derive what you need. Always works. Always.
No, but you can just like work with one, like the total energy on it.
Oh yeah, because they don't care about each other. If the temperature were going to change, say this was at 45 degrees Celsius, then I wouldn't have been able to cross the temperature out, and it would have been stuck here in our equation. But it would have still worked.
We use 25 on the first one.
Well, you have to convert it to Kelvin. But yes, yes, yes. It's other one I showed you where the logic came from. Okay, why you could do that. Yes, ma'am.
So we cross off the T up there and then you like, why did the arms?
Sure.
But will the mold ever change?
No, because you're taking the same moles out as you're putting in.
Okay, so we're not.
The moles you take out equals the moles you put in, provided you don't, your connector is good.
Did you say the temperature and volume is always constant? Or
No, you can adjust your temperature. You just have to include it in. The PV equal the P1 V1. The P total V total equals P1 V1 plus P2 V2. That's where your temperature has to be constant. Okay. All right. So Nikki, go back to where that R thing came from. Okay. I'm going to erase this. We know perv nert's a true statement. I knew the number of moles before and after wasn't going to change. What I take out, I put in. I know the temperature doesn't change. So R before is equal to P1 V1. Okay, now let's look at after. The temperature didn't change. The number of moles didn't change. So R after is equal to P2 V2. These numbers are exactly the same. Therefore, this is a true statement. 3 points. Anyone else? What?
I don't know.
Okay.
No, I'm good.
Mole fractions. It's good. Time to move on then. Mole fractions. Mole fraction always equals 1 to 1. I mean, it's always 1 because these guys are fractions. In a percent, what's the maximum percentage you can have? 100. So each percent adds up to the 100%. This is essentially the same concept. Each part will add to the whole. So instead of, using percents where we, times and divide by 100, this is, think of it as each part A plus part B equals the whole. And we, instead of using the whole as 100%, we say the whole is 1. Well, it looks, I mean, it's just a different way of looking at a percentage. We call it a mole fraction. We're going to be using moles, the number of moles in these equations. But the part has to equal the whole. That makes sense, right? Okay. And again, take a look at the mole fractions. Is this representative of the whole? The number of moles of A plus the number of moles of B.
Yes.
Does that represent the whole thing?
Yes.
Would this represent the part?
Yes, probably.
So your mole fraction, what is different between mole fraction and percentage of crap? What's the only difference between percent of something versus this? You're not timesing by 100. So your mole fraction can be thought of as a percentage, just skip the times 100 part. Okay, not a bad concept, right? It's part over the whole equals mole fraction. For percentage, it would be part over the whole times 100. It's just not going to waste their time with the... Because if you want to use a percentage, you're going to divide by 100 anyway, right? Might as well skip that stupid step. Don't worry about the... A solution has 1.43 moles of vanadium in oxide in that many moles of chloroform. Now, note the word solution. These are solutions. And if it's a solution, wonder if this is liquid or gas.
It's a liquid.
Most likely. This works for both liquids and gases, by the way. So what is the mole fraction? Ooh, typo. What is the mole fraction of each component? Well, we need our total number of moles. N total. How would I get the total number of moles? Add them together. So 1.43 plus 3.45 equals what? 4.88.
Yeah. It's always going to be equal to XA and XB. Like, which way you go.
Yeah, it doesn't matter. Okay, so that's what this number is down here. Just ignore all this math stuff. So to find the mole fraction of A, I take the part of A. Okay, I'm going to change A to say V for the vanadium oxide. You like that better? Mole fraction of the vanadium oxide?
Now, do we do sequence then? Or do we just...
Always, yeah. So you take the part that's A, which is the 1.43, divide it by the total, and you get that number. It's just like a percent, just not times by 100. Would there have been an easier way to have gotten the mole fraction of the second component? How? 1 minus. 1 minus 0.293, sure enough, is going to equal the mole fraction of the other component. Sure you could. The part that is B over the whole is that number. Well, that's easy.
You can always do A and then minus.
There's no units on a mole fraction, 3 points. No units for mole fractions.
That's the best part.
Of course, you don't really think I'm just going to stop there with an easy thing, do you?
We should.
Yes.
I'm not.
Oh,
Now, let's take a look at some derivations, because they're helpful. And even if the derivations, remember before, the derivations lost you a little bit, but when it came down to doing those problems, you were like, oh, this isn't too bad, is it? So if the derivations lose you a little bit, be patient with yourself. But this information does help with the comprehension of what's going on behind it. But don't freak out if there's so many letters you're like, just be patient with yourselves. So, true statement. The total the mole fraction, I'm going to erase this. Eraser. Okay, so if we take the mole fraction of, say, part 1, are you guys good with that statement?
Yeah.
The mole fraction of part 1 is the number of moles of part 1 over the total.
Yes.
And are you good with this statement where the number of moles would equal 1 and 2 and 3 and 4 and however many moles I have in my stuff?
Yep.
Part over the whole, no matter how much is in the whole.
Yes.
Okay, you're good with that.
Wait, so if there was like 5 of them, would we have to go through?
Oh yeah, you could find the mole fraction of all 5, just like you could find the part percentage of all 5.
If you find A, could you still just might?
No, we could, if you found part A, the remainder would be B plus C plus D plus however many others you have in there. Right, right. Well, is this a true statement?
I hope so.
Are you good with where I got that one? What do you think I'm going to do with N1? I'm going to substitute this for N1. It's going to look ugly. And would this be a true statement for N2?
Yeah, because N2 is.
I'm going to substitute it in there. This should have been a 3. Can I would that be reasonable? Can I take this?
Wait, why are you doing that?
I'm showing you where I'm going with this. Be patient. Can I take this and plug it in there? Is that fair? Is it reasonable? Good substitution? You're like, no, it sucks. Okay, so can I take this and shove it in there for N2?
Yeah.
And can I put that in for that? And I bet I could do this one into there, couldn't I?
Yes, but RT is constant.
Well, hold on. Be patient. So I know that looks ugly.
So it's
Very
that.
ugly.
It is very ugly. But watch this. What if VRT was a constant?
Just get rid of it.
It's one of the P2.
If that's a constant, your mole fraction can be used with pressures.
Whoa. 'Cause it would be.
So if you have the partial pressure of a tank of oxygen,
Yeah.
and you divide that by the total pressure in the tank, you can still get your mole fraction.
That would be your mole fraction? Like that'd
It
be a-
doesn't matter if you use moles or you use pressure. You can get your mole fraction either way,
So like, if I take
provided what 3 things are constant.
the
Well, 2 things.
volume and temperature.
Volume and temperature have to be constant, yes.
So if you just divide them, it
That's how you
gives
got
you
that.
your mole fraction.
Your mole fraction, yeah. So if you go back to those earlier problems that we did, the last one we just did, and you divide the partial pressure of oxygen, which was what, 2 point what? 2.63, was that the partial pressure of oxygen in problem 20?
Huh?
Was the partial pressure of oxygen 2.63 in the previous problem?
I think so.
2 point what?
Or wait, which previous problem?
20.
Yeah, it was 2.4.
2.4. And the total pressure was 11.6?
Yeah.
What's that equal?
9.2. I don't know.
No, it doesn't.
Point 2,
0. 0.2.
0.2. How many?
2's fine.
2, 1. 1.
2's fine. 0.21's fine. That is the mole fraction of oxygen.
And then do we still,
And if I had actually calculated it using moles, I'd have gotten the exact same number.
we still don't use any units?
No units on mole fractions. So what is the point of all that math crap I just showed you? What was the point?
You know the math behind it.
No, how do you?
No? I mean, that's helpful, but what was the point of what I just showed you?
Show us that we don't need it all.
I was supposed to.
You can use, using moles can help us find partial pressures. That's right. Nice job. Now, that's a 3-point answer. So here we go. The partial pressure of oxygen was observed to be that with a total atmospheric pressure of that. Calculate the mole fraction of oxygen in the tank. Hmm?
156 divided by 7.3.
Yeah.
Yeah. But let's get rid of the words. Okay? We have the partial pressure of O2 is 156 torr. And the total atmospheric pressure is 743 torr. So what is the mole fraction of O2? Well, we can take the partial pressure of O2, divide it by the total pressure, and we'll get the mole fraction. Who's got an answer?
0.27.
Yep. Any units?
No.
No units on mole fractions. Oh, how was that one for a problem?
Very
That
simple.
X is a partial pressure of that
This
one.
is how I like
That
one.
the X is the it's the Greek symbol chi, I believe, and it's what we use for mole fraction. Yes.
So basically the torr on the things just don't matter if you put it in.
No, because as long as they're the same, they're going to cancel out. It's a shift of multiplication and division, so that's why it works. Temperature wouldn't behave this way, but these do. 2 points, good question. Next. You do it.
Use times one.
I'm not telling you what to do.
I already did it. So
Mm.
Do it in torr.
Mm-hmm. What'd you get, William? 593?
do we not go to the decimal places?
Follow your well, it should have one more.
0.4.
0.4.
So far, that's the best thing we've done.
What?
So far, that's the best thing we've done.
Any other questions on this?
Astronomy? No.
All right.
Oh, now you know something else.
Mm-hmm.
Of course.
Of course we